Hello, you're back for today's talk about wind movement and ocean currents. You may remember in the last talk, one of the things we mentioned was the fact that the cells, the atmospheric cells that you can see here, are set up by the heating of air in the equatorial regions by the sun and the cooling of air create very cold, dense air at the poles, and how these two effects set up a series of high and low pressure bands that you can see in this graphic that's right here, as well as a series of winds that occur in bands where you have trade winds between 0 and 30 degrees latitude. Then you have westerlies between 30 and 60 degrees latitude, which is our latitude here in Washington, D.C. And then you have polar easterlies between 60 and 90 degrees latitude. So today, we want to explain why these winds are not due north or due south as the cells themselves would predict. You can see in this graphic that the winds are all angled, and they become either northeast winds or southwest winds in the northern hemisphere, or southeast winds and northwest winds in the southern hemisphere. So what is the cause of this angling? And that is actually difficult to understand because it requires a recollection of physics, and in particular, Newton's first law. So let us get started on that. It is the Earth's rotation that changes the direction of the wind. The Earth is rotating on its axis, as you know, and that is what changes the direction of the wind. The Earth rotates to the east, and the winds are therefore deflected from their predicted straight line path in the northern hemisphere. In the first cell, the tropical cell, the Hadley cell, the prediction is of a wind that heads south, so a north wind. But instead what we see is northeast winds because the wind is deflected towards the west and comes out of the northeast. This is due to what's called the Coriolis Effect. And the Coriolis Effect is the name for the effect that occurs due to the Earth's rotation. And the Earth's rotation affects the movement of fluids, of which air is one. The Coriolis Effect turns winds or water in the northern hemisphere to the right, and it turns them to the left in the southern hemisphere. So let's see how this works. Here is a picture, and imagine that a rocket took off from the North Pole. It was heading towards the equator. Now, as it moves south, it will be moving over Earth that is moving perpendicularly to it faster than it is moving in its left-right or perpendicular direction. The rocket's moving this way, but the Earth is moving this way, right? You can see this arrow here. And that means that as it moves, it's getting over Earth that has a faster and faster orthogonal, meaning at a right angle, velocity. Now let's stop and look at that for a second. So look here. Here is the Earth, and I'm going to set it in motion with eastward motion here. Here is the eastward motion of the Earth, right? And can you see that if you're standing here, you would go around this distance in 24 hours. But if you're standing here, you would go around all this distance in 24 hours. Therefore, a person standing on the equator is actually traveling in this direction. It's a longer distance in the same amount of time, so their velocity is faster than a person standing here. This means that when a wind leaves here, it does not have that eastward velocity. So a person standing here would have a smaller velocity than somebody on the equator, but would have a larger velocity than someone standing here. So as a result, as a wind travels this way, or as a rocket travels this way, right, the Earth will move out from under it. And what you will see on the surface of the Earth is the rocket traveling like this, unless it compensates its course, because it's losing to the increasingly fast Earth. So it is deflected. If you're looking at it this way, it is deflected to the right. Similarly, if you're moving north from the equator, you have the fastest velocity you're going to have in that orthogonal direction. And therefore, as you move north, you will be going faster to the right compared to the rest of the Earth, and you'll deflect once again to the right, which means you'll go this way, and you'll end up veering off to the right. That's what happens. It's hard to understand, but this is kind of a Newton's first law effect. Because when you leave the equator, you not only have a northward velocity, but since you were traveling orthogonally, which means at a right angle, with an eastward velocity, you have that velocity too, and there's no force slowing that down, so you continue to have that. And so as you move north, you outpace the Earth, and you deflect to the right.
So here's another way to look at it. Imagine a rocket that is launched due north from the equator. In this example, it has a northward velocity due to the rocket engine of 700 miles an hour, but due to the rotation of the Earth, it has an eastward velocity of 1,036 miles an hour, which is the speed of the Earth at the equator. That means that its total velocity actually would look like this here. It has a northward component and an eastward component, and the resultant would be a component to the northeast. And so if you think about it, as the rocket travels north, the Earth under it is getting slower. Look, by the time the rocket reaches 10 degrees north latitude, the speed of the surface of the Earth is only 973 miles an hour at the Earth, but the rocket still has, by Newton's first law, a speed of 1,036 miles per hour. So the rocket is moving to the east faster than the Earth is. As it continues north, it deflects more and more to the east relative to the Earth because its eastward velocity is greater. So that is why a wind leaving the equator and heading north would bend to the east, or alternatively, a wind coming south, a north wind, would bend to the west.
That is why we see what we saw earlier. And let me go show you that. Here it is. As the wind travels north, it bends to the right. As it travels south, it bends to the right. So winds traveling north, see that's a northward velocity component there, become southwesterlies, and winds traveling south become northeasterlies. The trade winds are northeast in the northern hemisphere, southeast in the southern hemisphere. So, I hope you understood that explanation. It is a difficult thing to understand. The summary is this. In the northern hemisphere, the wind is deflected to the right. Winds traveling south are deflected west. Winds traveling north are deflected east. In the southern hemisphere, the opposite is true. The wind is deflected to the left, so winds traveling north are deflected west, and winds traveling south are deflected east. So now we want to look at the overall effect of all this air movement on climate on Earth. Global air circulation has the effect of moving heat from the equator to the poles and bringing cold air from the poles towards the equator. So all this movement mixes the atmosphere. This means the higher latitudes are warmer than they otherwise would be without the wind, and similarly, equatorial locations are cooler than they would be if there were no wind. So what we have seen, due to all this air movement, as air travels over oceans or over land, its moisture content changes, its direction changes, and it is the interaction of these differing air masses with their differing histories that causes weather. And it's one of the reasons why weather is complex. In the temperate zone, weather is often caused by the interaction of polar and tropical air masses. And we see that all the time, as when a cold front comes through in the fall and changes us from a steamy day to all of a sudden a set of thunderstorms when the two air masses actually meet, and then the next day, crisp, sunny, low humidity days that so many people love in the fall because it's a break from that hot, hazy, and humid climate. And we are literally seeing two different climates there. On the first day, we have a tropical climate. On the second day, we have a polar climate. Now, the surface winds also influence ocean circulation. In fact, the surface currents on the ocean are most directly caused by the surface winds. And as a result, in each of the big oceans, the Atlantic, the Pacific, and the Indian, we get what are called the Great Ocean Gyres, and I'll show you a map of them in a second. For example, in the North Atlantic, the trade winds blow west, and the westerlies blow east. And this creates a giant clockwise surface current in the Northern Ocean and a counterclockwise gyre in the Southern Oceans. And a gyre is just a swirling mass. The circular pattern is also influenced by the Coriolis effect. So the winds which are affected by the Coriolis effect to begin with push the water in a direction, and then the moving water itself is affected by the Coriolis effect. And here's a picture. Look at here in the North Atlantic. Look at this in the Northern Atlantic. On the western side, you have water moving north. We know this as the Gulf Stream, and it's warm water. And then when it gets to Europe, much of it curls back around and then comes back down into the Eastern Caribbean, warming the whole way. Some of it moves up to go off Northern Europe. And this is why Northern Europe, at these incredibly high latitudes, the latitude of Labrador and north of Newfoundland, have incredibly mild winters. You know, snow is still relatively rare in much of England, and if you go over here to Canada, there's a ton of snow. So here are the gyres. Here are the 5 gyres that are set up: the North Pacific Gyre, the South Pacific Gyre, the North Atlantic Gyre, the South Atlantic Gyre, and the Indian Ocean Gyre. And this is a map of all the surface currents in the world. They're pretty fascinating. Now, one of the effects of surface currents that we're going to now study is the fact that what happens when trash that floats gets into these surface currents. Well, as you can imagine, if there's a gyre here, there's faster currents around the outside and slower currents in the middle. And so these gyres end up circumscribing giant patches of floating trash. And we're going to take a look in the next class at the Great Pacific Garbage Patch, which is a diffuse patch of plastic trash that occurs in the Northern Pacific Ocean. And here we have Hawaii, and here we have all the old Hawaiian islands that have now eroded to be nothing more than underwater or barely above water atolls or very small islands, including the famous atoll Midway Atoll, which had a very famous battle in the World War II in the Pacific Ocean and still has an airstrip. And we are going to look at these 2 videos. I ask you don't watch them right now, although you have access to them. We're going to look at these videos in class. And we are going to talk a little bit about plastic pollution in class tomorrow. That's it for today. I hope you feel like you've got a better understanding of climate than you did before. And if not, bring your questions to class. And until next time, study hard.